Hello everyone, my name is Kazuhiro Ida. I will make a presentation on generation of the individualized HRTFs in the upper hemisphere using Parametric Notch-Peak HRTF model. It is demonstrated that the direction of sound image can be reproduced by reproducing the listener's own HRTF. However, the HRTFs of other listeners often cause front-back confusion of the sound image and inside-of-head localization. The methods for obtaining HRTFs for individual listeners have been actively studied. Those methods can be roughly divided into the following two approaches. 1. Select a suitable HRTF from an HRTF database. 2. Generate the individual HRTFs from the listener's pinna shape. However, the localization accuracy is not enough for practical use. In the present paper, we propose a novel method that generates the individualized HRTFs for an arbitrary direction in the upper hemisphere using the Parametric Notch-Peak HRTF model for the zenith direction. The PNP model can continuously change the parameters of notches and peaks corresponding to individual differences in HRTFs. We demonstrated that the minimum HRTF components, which provide approximately the same localization performance as the measured HRTFs, were the two lowest frequency notches N1 and N2, and the two lowest frequency peaks P1 and P2, above 4 kHz. And each notch and peak can be determined by three parameters: center frequency, level, and Q factor by using peaking filter. We consider adaptation of the notch peak parameters of an HRTF to the listener. This is an optimization problem in 12 dimensions and is not easy to adjust by a listener. In order to solve this problem, we have proposed the Parametric Notch-Peak HRTF model. PNP model reduces the number of independent parameters, and PNP model can change the parameters continuously to correspond to individual differences in HRTFs by a listener. The frequency of each notch peak is expressed by regression equation with the N2 frequency as an independent variable. For the level and Q factor of each notch peak, the value averaged over 20 HRTFs was used as a common constant value among listeners. I will explain generation of individualized HRTF for the zenith direction. Here, we describe the 4 steps for individualization of the HRTFs for the zenith direction. A listener adjusts the N2 frequency while listening through headphones. Step 1. Use these buttons or slider to adjust the N2 frequency so that a sound image is localized in the zenith direction. Step 2. The Move button provides a stimulus with ITD and ILD added. Use this button to confirm that the sound image moves from the left side to the right side through the zenith. Step 3. Adjust the P1 level with +1 dB and -1 dB buttons. The vertical angle of a sound image rises as the P1 level increases, or decreases to the horizontal plane as the P1 level decreases. However, if the P1 level is lowered too much, a sound image is localized close to the head or inside the head. Step 4. The Save button outputs the individualized HRTF information as head-related impulse responses, together with the parameters of 4 peaking filters. Then I will explain generation of individualized HRTFs for the front and rear directions. In order to estimate the N2 frequencies of the front and rear directions, regression analyses were performed with the N2 frequency of the zenith direction as an independent variable using HRTFs for 20 years. The correlation coefficients between N2 frequency of the zenith and the front and between the zenith and the rear were 0.71 and 0.65 respectively. These figures show the relation between estimated and measured N2 frequencies for the front and rear directions. The abscissa is a measured N2 frequency, and ordinate is the estimated N2 frequency. The residual errors for almost of the years were under the JND. However, the residual errors for 1 and 2 years among 20 years exceeded the JND for the front and rear directions respectively. The mean absolute residual errors for the front and rear directions were 0.06 and 0.07 octaves respectively. Next, I will explain generation of individualized HRTF in the median plane. This figure shows that frequencies of N1 and N2 strongly depend on the vertical angle of the sound source. The N1 frequency increases with the increasing vertical angle of the sound source from the front direction to its above direction, and then decreases toward rear direction. The N2 frequency increases with increasing vertical angle from the front direction to the above direction, whereas the range of the change in frequency between above direction and rear direction is small. Based on these findings, the parameters of each notch peak in the median plane were obtained by interpolation using the parameters of notch peaks of the front, zenith, and rear directions. Finally, I will explain the generation of the individualized HRTF in the upper hemisphere. Previous studies have shown that sound image localization in the three-dimensional direction can be achieved by adding the interaural difference cues to the spectral cues in the median plane. Then, the individualized HRTF in the upper hemisphere were generated by adding the ITD and the ILD to the individualized HRTF in the median plane. We carried out the localization tests using the individualized HRTFs generated by the PNP model. The target directions were 7 directions in the right half of the horizontal plane, 7 directions in the upper median plane, and 7 directions in the upper transverse plane. The sound source signal was wideband white noise. The stimuli, which were obtained by convolution of the white noise and the individualized HRTFs, were presented to the subject through headphones. No compensation of the headphone transfer function was performed. The mapping method was adapted with a response method. 2 subjects participated in the sound localization test. These figures show the responded azimuth angles to the individualized HRTF in the horizontal plane. The abscissa is the target azimuth angle, and the ordinate is the responded azimuth angle. For both subjects, the responses were distributed around the target azimuth angles. For elevation angles, both subjects responded around the target elevation angle of 0 degree. These figures show the responded vertical angles to the individualized HRTF in the median plane. For subject 1, the responses were distributed around the target vertical angles for the target azimuth angles of 0, 90, 150, and 180 degree. However, the responses tended to shift to upward for target vertical angles of 30 and 60 degree. For the target vertical angle of 120 degree, the responses were distributed around 30 degree. For subject 2, the responses were distributed around the target vertical angles for the target azimuth angles of 0, 90, and 180 degrees. However, the responses were widely distributed for the target vertical angles of 30, 60, and 120 degrees. These figures show the responded lateral angles to the individualized HRTF in the transverse plane. For both subjects, the responses distributed around the target lateral angles. For the vertical angle, most of the responses of both subjects were distributed around the target vertical angle of 90 degree. Discussions. For subject 1, the responses to the individualized HRTF for the target vertical angle of 120 degree in the median plane distributed around 30 degree. Here we discuss a possible reason for this. Red solid line shows the individualized HRTF for the vertical angle of 120 degree, and the green broken line shows subject's own HRTFs for 120 degree. This figure indicates that the N2 frequency of the individualized HRTF was approximately the same as that of the subject's own HRTF. However, the N1 frequency of the individualized HRTF did not coincide with that of the own HRTF. In fact, the N1 frequency of the individualized HRTF for 120 degree coincided with that of the subject's own HRTF for 30 degree. This is considered to be a reason for the response distribution around 30 degrees for the individualized HRTF for 120 degrees. Next, let's compare the individualized HRTFs with the subject's own HRTFs for the target directions for which localization accuracy was high. These figures show N1 and N2 frequencies of the individualized HRTFs were approximately the same as those of the subject's own HRTFs. This might be a reason for the high localization accuracy. In general, N1 frequency for the vertical angle of 120 degrees tends to be higher than that for 90 degrees, as shown in the figure. However, the proposed individualization method did not reflect this tendency because the proposed method estimates the N1 frequency for 120 degrees by linear interpolation between N1 frequencies of 90 and 180 degrees. Then, we are trying for improvement of the localization performance by adding a PNP model for 120 degrees. We have developed the Orion 48-track 3D audio rendering toolkit using MATLAB. The Orion generates individualized HRTFs in arbitrary directions in the upper hemisphere using the PNP HRTF model and convolves the individualized HRTFs with the sound source signal. Final remarks. In the present paper, we proposed a method that generates individualized HRTFs in the upper hemisphere using the PNP HRTF model. The individualized HRTFs provided accurate sound image localization in the horizontal plane and the transverse plane. In the median plane, however, there is still room for improvement in localization accuracy. The Orion 48-track 3D audio rendering toolkit using the PNP model was developed, and multi-track 3D audio contents were created using the Orion. For trial use of the Orion, contact the authors by email. Now let's have a demonstration of 3D audio rendering. The music is the first minute of Till Eugenspiegel's Merry Pranks by Richard Strauss. You are surrounded by instruments. High-frequency strings and woodwind instruments are placed in the front. The brass instruments are placed in the above direction. And the mid-low frequency strings are placed in the rear. HRTFs were individualized by a female subject. Please listen through headphones. Thank you for listening.